Hey everyone, so in this video we want to talk about animated collision objects, because there's an important concept that you have to understand in Bullet, and that is the difference between an animated collision object and a deforming collision object. So what I have here is a simple setup. We have a couple of boxes here, nothing special, literally just boxes. And I moved them around so that they are here, stacked on top of each other, that I then assemble. So I have them packed now and they go into the active element. And then here I have a truck, nothing fancy, just some model I downloaded from the internet and assigned a couple of shaders to it. This truck is completely static, so nothing moves. And I animate it with a transform node. I use a fit function for this, by the way, which is a very nice trick. I'm not sure if I mentioned it before, but you can hand animate it. It doesn't matter how you create that. It just oops, it's a bit fast, sorry. So it just moves from A to B, nothing special. And if I put this into my collision geometry here, into my second input from the right, you can see that everything seems to be okay, but when I press start, nothing happens. So the collision object here is not moving right now. Now the reason is that under collisions we can see that our collision type currently is set to animated, and this is a bit confusing. This is exactly what we want to talk about here. Let's see what else we have. We have static. Okay, we don't have to talk about this. A static object, it's just something that doesn't move. And then we have animated and deforming. And this is something that is important to understand. Animated is the default, and you would think, well, that should recognize my animated truck because obviously it is animated. But animated in the context of Houdini, or specifically the context of RBD, means something special. It basically means that a packed geometry is animated, not the geometry itself. So what I mean by that is currently what we have is a truck that is built of 26,000 points roughly, and then we animate all the points through space. So every single point of my truck right now is moving through space. And that actually means that not the truck as a whole is animated, but all the points that are part of the truck are actually moving in a certain direction. Now this technically is actually not an animation in Houdini, but this is a deformation because we are basically deforming the truck in space. And this is why we have to actually tell the RBD bullet solver that our collision type is actually deforming. It is a bit weird, but this is actually how the RBD bullet solver thinks about these things. So if we press start now, you can see that our animation is actually considered. But there's a problem with that approach, and that is it is actually pretty slow, first of all. So if you look at our frame rate, well, actually, as long as we haven't cached the whole result, so let's delete our simulation cache by pressing Control and then left click on our little brain down here. And if I press start again, you can see we are roughly talking about 4 frames per second. And the reason is that basically the bullet solver now has to calculate the collision representation that we've actually haven't seen yet. It looks like this for every single frame, because every single frame we basically give the bullet solver a new geometry, a deformed version of our truck. And this is highly inefficient, and also it actually results in errors. When you look at the result and you look at the boxes here, they actually, well, it's a bit fast, but you can see they actually move below our truck into the ground. And you can see that there are interpenetrations, so this really looks bad. And you would see that when you would render this. Now, to be fair, you can actually solve this problem in a brute force way. And that is by just increasing in the RBD bullet solver the global substeps. So let's increase the substeps to 5, let's say. And then if we rerun this, we can see, of course, the main problem here is it's now much slower, but at least the collision problem is gone. So we will not get any interpenetrations anymore. But nonetheless, there is a better way of doing this. So let's set the global substeps back to 1, and let's talk about the actual most efficient way to solve this problem. And this is actually the reason why the collision type is set to animated. Now, animated would mean, like we said, that we are not moving every point of our geometry, which the transform node is actually doing, but we want to move the whole thing as a whole. And you might already guess how to do this because we use this so often already. We just pack the whole thing. So if we pack our whole truck as one object, and then we transform the whole thing, then we only move a single packed geometry through space. Now be careful. If you now press start, you can see that we basically have the exact same result as before. A little bit faster actually. Yeah, now we have 8 frames per second. But we still have the collision problems. So the result is still not very good, as you can see here. By the way, I'm not sure why our truck suddenly changes from blue to white. I don't know, but here we go. Here you can see there's still problems in the collision calculation. And the reason is that I forgot to change the collision type back from deforming to animated. So be careful. Just because you have a packed geometry animated doesn't mean it will automatically use the animated version. It still uses the deforming approach, which still has all the disadvantages. So let's switch this back to animated and reverse, and let's run this again. And you can see, first of all, it's much faster. So let's turn off the real time, because it was faster than real time actually. If I press start, we're ending up with something around 40 frames per second or 50 frames per second. So significantly faster. That's the first advantage. The second advantage, which is actually more important, is that we also get less collision problems. So as you can see here, there's actually a correct calculation of our collisions. And that is because basically, since the bullet solver doesn't have to rebuild the collision object every frame, there is a consistency now in the subframe calculation. So this concept obviously is tremendously important. By the way, let me just unpack the whole box and then take the original truck so that we can see the whole thing with shaders. This is now super fast and also super accurate. So this is why it's super important. Now this whole concept comes with a problem though. In this case, it was easy for us to solve this problem because we had the truck and we animated it ourselves. So packing it before we animate it was easy, no problem here. But what do we do if this comes actually from the animation department and potentially has much more complex geometry that is involved here? So to simply show this, let's just assume we have an animated version of this truck where the movement is already part of the geometry. So if you bring this in, we don't need the transform anymore. We instead use a truck animated directly. Of course, we have the problem again that the animated collision type doesn't work anymore, obviously. So maybe you'd think now, okay, let's just pack the whole thing after the animation. Technically, that actually works. When we look through the viewport, we can see that the animation is not lost. But what's happening here is that we pack again every single frame of a deformed truck. So even though we don't see it here, every frame we create a new packed geometry. And this is why in the RBD bullet solver, when we keep it on animated, this is actually not working. It's basically the same as before. We just have a deformed geometry that we pack every frame. So this approach is not working. What are we doing in this case? Well, there is a solution for this. So we don't need the pack. And that is actually very well named by side effects. There is a node called RBD Deforming to Animated. And this node takes care of making sure that a geometry that comes in that is deforming is actually turned into an animated version. So when we middle click, we can see, okay, this is throws an error. Let's deal with that first. It actually tells us that there is a name attribute missing. And this is important. For this to work, we need a name attribute. Now we could use an assemble node here, but I would be careful with this because this truck here is made of multiple objects. So an assemble node would technically create multiple name attributes from name 0 to name 140. This would still technically work. As you can see here, it would just create 144 different objects. This would still be very efficient. So if I run this, you can actually see when I reset the simulation that this is still pretty fast, but it's only 20 frames per second. A bit better could be to just not use an assemble, but just create a name attribute directly for the whole thing, because there's no reason why we would separate them. So let's just call this truck, and then the RBD Deforming to Animated will just create one point based off the name and turn this into an animated version of it. And now when we run this, the whole thing is even faster. So in this case, it doesn't actually really matter if you use an assemble or a single name attribute, but there are cases where it makes a difference. And that is when you have elements that are animated in of themselves. So for example, this helicopter here that we will see later on, when this is moving, you can see that certain parts of the geometry are animated. What's important here is that the point count should not change. So when you have something that is deforming, it should not change the point count, otherwise the system will not work. And also you should make sure that your geometry is not deforming in itself, so actually changing its shape. This is, yes, this is rotating, which is fine, but it's not, bending or something. So in a case like that, you need an assemble node, because this assemble node will then make sure that every single piece here is considered separate so that the rotor, for example, can move separate of the body. So in a case like that, you have to use an assemble. So if we now use a deforming to animate it, you can see that it finds 399 different objects, because it can calculate here now even the rotation of our objects. And when I talk about rotation, you guessed it, this is now actually not only calculating the velocity of a single object, but it even is able to recognize the W, so the rotation of an object. But this again is only possible if your geometry, like here, is not changing its point count and not a deformation where the actual shape of the object changes. I hope this makes sense. So as you can see, it's clever enough to actually now find our animated rotation and turns it into a W, which is really cool. And if you would leave the assemble out, so you would not have a proper name attribute set, or in this case, actually there is a random name attribute that is not correct actually for all the elements, you can see you would simply lose your animation. So this is why you have to be careful. If that happens, make sure that you use an assemble to recreate the name attribute for every single object. Remember this because we will see this helicopter again in a later chapter, but for now let's keep it simple. When you have something like a single object that is not animated inside of itself, then a single name attribute, as we have seen, is just fine. Now, before we finish this video, I want to emphasize one thing again. I briefly mentioned it, but I want to make this clear again. This technique only works for objects that are in themselves not deforming, so not changing their shape. So here this car, usually a hard surface object is like that, is not changing its shape, it's just moving around. Same is true for the helicopter. The pieces are not changing by itself. Yes, they are transforming, but a blade, for example, is not, moving in a wavy shape or something. So what we have here is something that does not change in shape. A case like that would be something like, for example, our horse that we've seen before. So when you look at the points that our horse is made from, then you can see it's actually changing the relationships between them. So this is actually a deforming or shape changing geometry. The technique we just learned will not work for something like that. This is also true, by the way, for objects that change the point count over time, which is rare, but if you have something like that, forget it, this will not work. But in a more common case like this, that we have actually deforming geometry, usually that's characters, creatures, or animals or something like that, I will create a video about this topic called deforming geometry in the bonus RBD chapter. So have a look there if you have a case like that, but since this is a bit more advanced, I didn't want to put it into the basic subchapter. So keep this in mind, everything I explained so far usually is meant for objects that do not deform in themselves. So usually hard surface objects like cars, planes, helicopters, spaceships, stuff like that. For everything else, have a look at the bonus chapter. So as you can see, this whole thing is very important to understand in the context of Bullet. And whenever you deal with animated collision objects, you should look into the whole topic of animated and deforming. Keep in mind that this is very important when you deal with animated collision objects, but later on we will look into this also in the context of active objects. So try to keep the logic or the definition of animated versus deforming in the context of Bullet in mind, what it means in Bullet, because later on we will see this whole topic again. But for now, I hope this is helpful. So thanks very much and see you later. Cheers.